Let us now look at an example that is not a polynomial. Let's look at the following problem. Sketch the graph of f of x equals x minus 1 over x minus 2 natural log of x. This is clearly not a polynomial. This contains this negative power function and also this natural log. So what is the domain? X is defined everywhere. Minus 1 over x is defined when x is not equal to 0. But natural log is only defined for positive numbers. So this is defined where x is greater than 0. So that's r plus, or the non-negative real numbers, minus the origin, minus 0. Let us notice also that when x is equal to 1, this is equal to 1 minus 1 over 1. If x is equal to 1 minus 1 over 1 minus 2 times the natural log of 1. What is the natural log of 1? Is 0. We need to raise e to the 0 to get a 1. And this is equal to, and so this whole thing is actually equal to 0. So that gives us a 0. Now that we have a point, an open, this function is defined in an open interval, so we reach an endpoint. We need to analyze the behavior as you approach that endpoint. So what happens when we approach 0? The function is defined only when x is positive, so the only thing that makes sense here to possibly detect vertical asymptotes, to take the limit when x approaches 0 from the right. So this is what we have. The f of x, limit of f of x is the limit of x minus 1 over x minus 2 natural log of x. And here we factor out minus 1 over x. And then we get 1 minus x squared minus x minus 2x. It's 2 times x times the natural log of x, and this is equal to, well, let's look at this. This is approaching minus infinity, because you're dividing 1 over something very small, but it's positive, so that the 1 over x is approaching 1 plus infinity, but minus that will turn it into minus infinity. Now what happens with the second expression here? The second expression is becoming it's becoming closer and closer to 1. 1 is 1. X squared is going to 0. And what about x times natural log of x? Let me write it over here. So x natural log of x goes to 0 as x approaches 0 plus. And this is a consequence. If you go back to this is a consequence of L'Hopital's rule. Okay, so that it follows from L'Hopital's rule. You have 0 times minus infinity. And if you remember, what we did was to, I told you to always leave the natural log alone. So this is natural log over 1 over x. So this is infinity over infinity. Okay. So in sum, this whole thing is approaching, well, minus infinity times 1. So it's not an undetermined form, because, well, x squared is approaching 0. 1 is 1, and this is approaching 0 as well. So this whole thing is just minus infinity, the limit. So we have a vertical asymptote at the origin, Now the limit as x approaches plus infinity, I mean it's equal to infinity, it's not approaching really anything, it's just becoming unbounded, of x minus 1 over x minus 2 times the natural log of x is, and again we now factor out by x because that's what's becoming bigger than anything else. As x goes to infinity of x times 1 minus 1 over x squared minus 2 times the natural log of x divided by x. And again, x is going to plus infinity, this is going to 1, this is going to 0, and this last term can be also shown to go to 0, thanks again to L'Hopital's rule. So this is approaching plus infinity times 1, which is just plus infinity. So, well, it's not approaching, it's just increasing without bound. Okay, so we have, there are no horizontal asymptotes then. There's a vertical asymptote at the origin, and there are no horizontal asymptotes. Now, let's look at the derivative. Remember that the information about the shape of the graph is going to come from the first and second derivative. So it's 1 plus 1 over x squared minus 2 over x. Remember the derivative of the natural log is 1 over x. And this is exactly equal to x minus 1 squared over x squared. Okay, if you don't believe that, you can expand x squared minus 2x plus 1 divided by x squared. And if you separate this into 3 terms, you get x squared over x squared, which is 1, minus 2x over x squared, which is minus 2x, minus 2 over x, and plus 1 over x squared. Alright, so f prime then will be, f prime then will again be equal to 0 when x is equal to 1. And only when x is equal to 1. So the only critical point, so if we're looking for critical points, we need to set f prime equal to 0. F prime of x equals to 0 if and only if x minus 1 squared divided by x squared is equal to 0. And we made this comment a number of times during the semester. Fraction can become 0 if and only if the numerator is 0. So if and only if this is equal to 0. So this gives us x equals 1 as the only critical point. F prime of x f prime of x is actually otherwise, I mean, if x is not equal to 1, then f prime of x is going to be positive. Why? Because, well, we have a squared over a squared. So squared, so this is a square, so x minus 1 over x squared, and that's positive unless the numerator is 0. And that only happens when x is equal to 1. So as long as x is not equal to 1, and x is positive because that's the domain of definition of f, then f prime is going to be greater than 0. So that means, so this implies that f is increasing everywhere. F is increasing everywhere in its domain. F is increasing everywhere in its domain. Everywhere in its domain. Okay, and from its domain. So we have a function that is always going up. Now we need to retrieve the information about f double prime. F double prime is now minus 2 over x cubed plus 2 over x squared, which is equal to 2 times x minus 1 over x cubed. And here again, I mean, we just see that the 2 over x squared comes from dividing x by x cubed multiplied by 2, and then the second term is minus 2 over x cubed, which is here. Okay, so we need to find the points where this becomes undefined or 0. And in the domain of f. So f double prime is equal to 0. It's equal to 0 only when x is equal to 1. Remember, again, the same thing. For x equals 1. A fraction is only 0 if the numerator is 0. So f prime of x is 0 only for x equals 1. And f double prime is greater than 0 when x is, x cubed is always positive if x is positive, so the sign of this expression here depends only on the numerator, and numerator will be positive when x is greater than 1 and will be negative when x is less than 1, so between 0 and 0 and 1. So double prime of x is positive for x greater than 1. F double prime of x is negative for x between 0 and 1, so x between 0 and 1. And f double prime is 0 only when x is equal to 1, which we already recorded. So these are the main elements here, the main things we can get out of analyzing f double prime. So what this implies here is that the function is concave down between 0 and 1, and then becomes concave up. So that means that x equals 0 is a point of inflection. So this implies f is concave up. It's concave up. On 1 comma plus infinity, and the second statement here says that f is concave down, concave down, on 0, 1. So we have our points of inflection, and we have the point of inflection, the critical point, and we know, I mean, that f prime is actually always increasing. We have a vertical asymptote that is coming from the fact that the limit of f as you approach f as x approaches 0 is minus infinity, and so in the end the graph but let me just remind you of something here before we move on to the drawing. So all this information here implies that 1 is an inflection point. Okay, so it's an inflection point. Okay, so that we'll need to take that into account when doing the graph of f. So this is the y-axis, this is the x-axis. We know that at 1, the function is equal to 0. We first recorded that at the beginning. Yeah, remember, it's exactly here. F of 1 is equal to 0. So we need to make a graph pass through 0. We also know that the function is increasing here. It's actually increasing at every single point in the domain. But we also know that it is approaching minus infinity as you approach 0 from the right. And you know the function is concave down between 0 and 1. So it must look something like this. Okay, so this function here is concave down. It's approaching minus infinity. It is 0 at 1. And at 1, you also have a critical point. So this slope here is 0, so this is tangential to the x-axis, and the graph continues to growing like this. So remember that f prime is positive everywhere except at 1, so f is increasing everywhere. But here we draw the graph like this because f double prime is positive, so the function is concave up for x greater than 1. Otherwise we would have drawn something like this. But the function is concave up. So this is the shape of f. We recorded all the relevant points. And what about 1 again? 1 is a 0. It's a critical point, and is also an inflection point because f double prime is equal to 0 there, and it changes concavity. So between 0 and 1, the function is concave down, and from 1 to infinity, the function is concave up. Okay, so okay.